Tool changing, woo! Okay, let's put this out right at the start. This is not a product, right? You cannot come to me and purchase one of these. I do not want to get into the game of selling 3D printers or competing with these guys. That would be a terrible idea. This is a reference implementation for a concept that we want to do. So we are taking pre-orders, and what you pay us $100, it gets you a place, $100, pounds, whatever. You pay us 100 units of money. It gets you a place in the queue. The place in the queue, yeah, we should accept Bitcoin too. You know, pay us 100 Bitcoin. We get you a place in the queue. We don't know how much it's going to cost yet to make in the volumes that people adopt it. So at the moment, we've sold like 150. Once we get to about 300, there are some good price breaks there. So once we've figured out how many people are going to buy them in 2 months' time or so, then we'll be able to tell you how much it's going to cost. How much it's going to cost on top of your $100 to fulfill the rest of the order. And so what you will receive is everything you see here with no electronics and no tools. Now there's a method in that madness. One is it stops idiots from buying one, because this is not a consumer product. It is like a research platform, and it is a reference platform. The other point is that there are lots of potential electrical solutions like Redeem and Clipper and Beagle boards that Lulzbot are working on, and I think the guys over there with the hat are working on 32-bit, if my rumor hears me correctly. Is that right? Are we talking about that yet? No? Yeah, we're not talking about it. I'll say nothing. Really? Beaglebone? Beaglebone? Nice. Anyway, yeah, we recommend Duet because they rock, and the Duet concept of scriptability of G-code really allows us, we could not have made this machine without Duet Electronics and their software stack, because it allows you to do these crazy things like have macros and scripts and conditional G-code, and it's amazing. Thank you to Tony. Where are you? Yeah, thank you guys. They are one of the best electronics in the world. I can't be biased because then these guys will be like, our electronics are better. But if you want to build a crazy machine that is non-standard, these are definitely the best electronics in the world. They let you can do anything with them. So yeah, no electronics. It does come with the motors because it uses special motors and integrated lead screws. It doesn't come with the tools, and the reasoning for that is that each printer is going to be for an application-specific purpose. You may want to have just a carbon fiber reinforced peak extruding volcano and a support head, or you may want to print all flexibles, or you may want to have a camera on there for inspection. We'll get into all of this in a minute. But buying the tools separately, because it would be silly for us to supply it with just 4 V6s, as it is now, which is kind of like the boring version. It's going to let people build application-specific 3D printers, which I think is really cool as a concept. And most of you guys have hot ends and electronics and things like that. So hopefully it lets you kind of build and play. So yeah, you need to add electronics, you need to add tools. It'll be open source, obviously. No way that this would work without being open source. Yeah, the motion system on this rocks. So this is an exercise in my day job is making sure that hot ends get out to people like Joe and people like Lulzbot, and then Greg and I, who's the silent hero, come in on the weekend and we pursue these crazy projects. So this is our weekend passion project. And it's kind of an exercise in, if you write a blank check, what can you build as a 3D printer? And we're very privileged at E3D to not quite have a blank check, but to have enough to build a machine like this. What you're seeing up there is not cherry-picked data. It does this every time. And bear in mind that the tolerance stack in all of this, we're moving Z, we are moving X, we are moving Y, we are dropping off the print head, we are picking the print head back up, we are returning over and then putting the nozzle back down on the dial gauge. And the ball of the dial gauge is centered on the nozzle orifice. So if it was off in XY, it would also misread. So yeah, that's pretty good, I would say. I actually had to buy a more precise dial indicator, a digital 1 micron one. So it looks like we get repeatability in the order of about 3 microns. Our error budget was 50, so I think we did it right. So yeah, that worked. So it's based on Core XY with the Fab Totem planar belts setup. I won't go into that. They wrote a great blog post on it if you're interested in it. I think it's one of the more popular and logical ways of doing Core XY. There is still a moment applied, but that moment is applied at the head over a very short moment arm, which is the distance between the 2 belts. And we're running preloaded genuine high wind rails up there, so the deflection isn't. So that's all good. Splashed out on the carbon fiber gantry bar, weighs 120 grams. It moves like feces off of a shovel. Like, it goes. Yeah, it wasn't actually that expensive. It was like, it was under $100, right? So for a punt, like, it's worth a go. Actually want to carve more weight off of this by using Nomex foam sandwich panel, which I've got a bunch of back at home, and I need to buy myself a Shapeoko to cut them out and play with them. Because we can't actually cut this whole thing on our normal machinery, because we're like, our machinery is built for cutting like blocks and stuff, you know, tiny things. So yeah, I'm going to get a Shapeoko and then try it with the Ultem foam sandwich panel stuff, which is, it's like half the weight. I think we get it down to like 60 grams. And so when you see those insane like Ultimaker moves, we should be going faster than that. Also, we're putting like bigger motors and better drivers. I think we want to put Mechaduinos or something on it, like, and then we'll be moving. Then we'll be really moving. High wind rails are amazing. I'd only played with the cheap Chinese knockoff high wind rails, and I played with a bunch of them, right? But the genuine high wind rails are astoundingly better. Like, the mind, like, you pick them up and you feel them and you immediately understand how much better they are. They are insanely good. And they're not that expensive, actually. I think it's like $18 for a carriage, something like that. $18 for a rail, so you know it's money, but it's not like too much money. Worth it. We struck up a relationship with Gates. They're a great company. We're using Gates genuine GT2 belts and pulleys. Someone pointed out that we should use toothed idlers as well, and they explained their reasoning, which is that the flat idlers actually flatten out. Who was that? Was that someone in here? Anyway, thank you for the advice. We're going to try that out, see how it goes. But yeah, the Gates belt really reduces ringing. They put a lot more aramid in than the Chinese GT2 belt, and the aramid is the stuff that provides the tension and stops things slipping. The Z-axis on the new version, this is V1, the new, is it over here? We'll get it. Yeah, on the new, this version uses 2 rails. We wanted to like keep it consistent and use the same type of rail on X, Y, and Z. But then that dream was shattered because we wanted the really lightweight rail on X to keep things light. And so then we were like, screw it. So now, instead of having 2 rails that are a pain in the ass to tram. We just got like one big, we were like the biggest high wind rail that they'll do, like with all the preload on it. It's good. It's really good. And that's driven by a really, really nice integrated lead screw motor. And so you see in that tolerance stack, it's doing its job well. There is no Z wobble. It's a cantilever bed, controversial decision. Had to fight that one out with Greg for a while. But FEA shows that it works. I want to put that one through some like top-up, generative design or something, see if we can do it any better. So the initial results of the survey indicate that this thing's going to be too expensive to attract most of you people. All in all, to get the thing to you with no electronics and no tools, it's going to be like just over $1,000, like $1,200. Then you've got to add the electronics. Like, how much is a duet? 100 and plus the Duex 4 thing. And so that comes to, so we're now up to 1,500 plus, you know, 50, 60 bucks per tool. Like, it's an expensive machine, right? So we're contemplating making a cheaper version. The cheaper version will be exactly the same design in every way. All that we will change is the materials and components and their suppliers. So we will cut the top frame out of Dibond, which is a really cool material. It's a composite sandwich panel. Really good for structure, and they do a structural grade, which is like 1/2 mil of aluminium and then polyethylene and 1/2 mil of aluminium. It's really nice and fast to machine, and it's cheaper than aluminium, should get costs right down. But it's stiff. It's really, really stiff, especially like in the, because this plate only needs to resist forces in this direction, and the stiffness of a cantilevered beam is it the 4th or the 5th power of its cross section? Anyway, it's in, like, sheet material is basically infinitely stiff across the point of the sheet. So like Dibond or aluminium, it's all going to be fine. Replace the high wind rails with tri-wind rails, but we've got a tried and tested supplier for those, and use the clone belt. It's still quite good. Z-axis will still be hardcore, and it will still be one big fat tri-wind rail. It will use the same lead screw, and it will use the same bed, and we will be trying to FEA optimize that for DFM. No idea of how much the repeatability will be affected. Maybe it won't be at all, and we'll just scrap the expensive version. I don't know. But can I ask for a show of hands here? If we got, excluding electronics and excluding all tools, if we got it to below $1,000, would you buy one? Put your hand up. 900? 800? Keep your hand up if you're still in. 900, 800, 700, 600, 500. All right, so we need to try and make it $500, Greg. I don't think we can do 500. I reckon, what do you reckon?
750 maybe.
750, I was thinking 650. I reckon we can get it around there. And maybe we can do a kind of, maybe, pardon? Say what? Pounds. Yeah, flat packs really nicely. Like really, really nicely. You take off the extrusion, it all flat packs. Yeah, it's gorgeous. Yeah, I reckon we can do it at, $750 thereabouts in Dibond. Yeah.
What about just selling like a kit of the parts that are for the tool change?
Yeah, lots of people have asked me about that. Who would be interested in that? All right, so we need to do that then, huh? So, yeah, we're kind of figuring this out. So we're working with So Lulzbot have said that they're interested. BCN 3D have said that they're interested. We want to work with those guys to develop an open standard such that you can take a toolhead from a BCN machine, drop it on a Lulzbot machine, and it'll just start printing. Open source standard. And we'll make tools. Anyone else can make tools. We make the best tools, so you can, you can choose who you can buy them from. But that's the intent. Don't know where that's going yet. There's still in discussions with BCN, still in discussions with Lulzbot. Who knows where that goes? We will definitely produce. Maybe we'll do a beta phase grabber, and yeah, we should do that because that's cheap, right? We can do that whole. If you get rid of the high wind rail and just do the carriage. Yeah, that's like sub $100. So you can do that for like $50. Yeah, for the grabber, and then the plates to pick up the parts are.
I'll take 2.
Yeah, the plates on. So we're going to skip through here. So this is what the tool looks like. So this is a high temperature volcano for printing PEEK through a hardened steel nozzle, carbon fiber reinforced. Anyway, what we have. Is the mouse on that? Yeah. So this is just laser cut aluminium. These are machined aluminium at the moment, but we're going to make them out of case hardened ground steel because, yeah, it's not that much more expensive, and it means that basically aluminium frets, and over time the calibration will move by like a few microns, and that wigs me out. So we're doing them in stainless. So that's cheap. Like the water jet cup part's like $3-4, and then the little bits on the end, we make custom tooling to cut the groove. So it's like a wham bam, one pass, thank you ma'am job with 2 tapped holes. So those are like a couple of bucks a go. So those can be probably like $10 for that plate. That's what we're talking about, that plate. And then you can build whatever tool head you want off of that. So you're like $10 a plate. And then there's the coupling system. We'll come back to that. How not to pick up a 3D printing tool head. And now I don't mean any offense to people who have tried these methods, but I want to explain our reasons for not doing it like this. Magnets, particularly permanent magnets, you do not want to interfere with the kinematic coupling system. Kinematic couplings are a gift from the great gods of Lord Kelvin and Maxwell, and you do not want to interfere with them. You need to provide 6 exact constraint points of contact. We'll get into that in a minute. But magnets interfere with that and apply forces in ways that you don't want. Electromagnets are cool, but they generate a lot of heat, and they actually take up a lot of space, and they interfere with other stuff on the print head. The electropermanent magnets, we tried, guys, we really, really tried. You can't get the guy to make them. They're big, they're heavy, and they're really expensive. Whereas a servo is like $3, or you can buy like the $5 one. It weighs 5 grams. You print some gears, and then you put the little latchy bit on the front with a spring, and you're kind of done for like $7. Whereas the electropermanent magnet thing, how much was it? Yeah. So, yeah, and our solution, so what we've come up with is it's cheaper. We should be able to build the whole thing for, I don't know, $50 or something. The grabber, that is, for less than $50, which is the cost of one electropermanent magnet. And it's 1/3 of the weight, mass, and volume. So yeah, it's a bit better. One thing that I had really close to my heart was the vacuum grabber. So it was basically a plate with a quick detach fitting on the back, and then there was a gasket made of foam, a silicone closed cell foam gasket, you know, the kinematic coupling elements in there, and it would go up to the tool, because this is how they move panels in automotive production with these suckers, and lots of conveyance is done like that, like silicon wafer conveyance. So I was like, that's the way to go, right? It's also super lightweight because it's like the Bowden system of doing it, because the vacuum pump is off to the side and you just run the hoses up there. And if you have that small area, and even with El Cheapo Chinese Alibaba pump, you get like, I don't know, 10 kilos separation force. It's good. Problems, like you get a little bit of dust in there, or, you know, like we call it print cheese, like the crap that comes off printers, right? That stuff. If you get that in there, it breaks the seal. It also doesn't give you much in the way of like redundancy, because as soon as you break the seal, it's game over, the tool falls over, and then everything's not gone well, because you've got this open loop printer running around smashing into things with this pneumatic head sucking onto things, and I like the idea. It didn't come to fruition. The idea was that the closed cell silicone foam would be compliant enough that the kinematic coupling would be able to settle into place. That wasn't quite the case. It was a little bit touch and go on that. And yeah, the pump was noisy and quite expensive, or at least more expensive than a servo. And it means that you have to run tubes to your head, which is a bit of a ball ache, and you've got all the pneumatic fittings and stuff. It all adds money and cost, whereas servos are cheap, and also you can plug a servo into pretty much any standard 3D printer electronics and it works. So clicky clacky latchy mechanisms, which are a whole class of mechanisms whereby they work kind of like a ballpoint pen. You know, you go over to them, you pick them up and they click into place, and then you go back over and you plunk them off, or sometimes you kind of go over and you slot them in sideways and pull them back out and all of this kind of stuff. Our reasons for not going with that is that we needed the kinematic couplings to get the precision, and these clicky clacky latchy mechanisms necessarily violate the principles of exact constraint that I will get into in a moment. They also reduce because you have to, with most of these clicky clacky latchy mechanisms, you have to go in, move sideways, and then pull out, because you have like something like a button head screw in it that goes into a slot that's got a wide hole at one end, and you pull it off and it settles. So you actually reduce the number of heads that you can cram in the machine, and you have to do all this complex motion, and yeah, I just didn't enjoy it so much. There are some nice systems that do that out there, but they don't exploit the principles of exact constraint, which is what gets us off 3 microns, and that's the kicker here, right? So how the whole thing works. Hands up if you've heard of kinematic couplings. Cool, all right. And the principles of exact constraint. Yeah. If you want to learn about this, there is a great series of lectures written by a great guy called Alexander Slocum. And also there is an amazing PhD thesis that was written by L.C. Hale while he was working at Lawrence Livermore National Labs. So they rediscovered these two concepts that were invented by Lord Kelvin, British man, and Maxwell. He was British too, yeah, British too. They came up with these things. The one on they both provide exact constraint. The principle of exact constraint is that any object has 6 degrees of freedom. You have 3 translational degrees of freedom, And then you have 3 rotational degrees of freedom. And you need to remove each of those degrees of freedom in order to get exact constraint. And if you do that exactly right, then you get very precise systems. So you'll note that these balls drop into these grooves, and they make a point contact there, and there, and there, and there, and there, and there, and you get 6 points of contact. Those points of contact are convergent and also in different directions, so you get exact constraint. All you need then is a system to hold them together, which could be a magnet or an electromagnet. In our case, we went servo. It blew my mind how well they worked from the first time we put them together. So our first prototypes were basically made like from an old V6 heater block with a file to cut the groove in it, and then like some sandpaper. And that is what was in that video showing you the 3-micron repeatability. I'm excited to see what happens when we move to ground, like, and our faces are going to be ground case hardened steel, which we will coat in a slippery but hard surface so that they settle properly. So yeah, so it's not like we need to go better than 3 microns, but I mean, if you're going to do it, you may as well, like, yeah, go hard or go home. We went with, so this is Maxwell's implementation. This is Lord Kelvin's implementation. They both do the same thing. We went for Maxwell's because it's easier to manufacture, because you just make lots of these, and balls, balls are not hard to make. Humanity's managed that thus far. So here you see the horrible gash made with a file. Not insulting your manufacturing friend or anything, but they're not gorgeous. But we get 3-micron repeatability off of these. Like, I don't know if I can zoom in on this. Is that? Oh God, I've done a horrible thing. Can I zoom? I'm not going to zoom. All I will tell you is that the surface finish on these and the hardness on these is not so great. It's like T4 temper aluminium, so it's kind of hard on the aluminium scale, but it's still aluminium. It's not steel. It's been case hardened and ground. So yeah, that's what a tool looks like. This is an interesting tool because it's a volcano. You can have a V6, you can have a volcano, you can have other things as well. How do you pick up the tool? Now, here we've got a slot. And we wanted to keep this object 2D manufactured, like in terms of like base principles of manufacturing. If you can make it out of a 1-dimensional material like wire, that's the cheapest. If you make it out of 2-dimensional material like sheet, that's the second cheapest. You have to make it out of 3-dimensional material like CNC milling or 3D printing, that's more expensive. We wanted 2D manufacturing on this part, so this is just a slot. Then there's this thing. To get it done quick, we had this DMLS prototype by Shapeways, and it's stainless steel, and we plated it in gold because, you know, the object, you know, money is no object, and it's gold, right? And so that was fun. Now, what you can't kind of see is that this isn't just a T-bar. So this T piece here, can you see my mouse on the screen? This T piece goes into that slot, and then it rotates. Now, watch more carefully. The T piece is not just T-shaped, it's got angled cam surfaces on it, and it's on a rod that is sprung. So what happens here is I'll hold my finger here, or maybe I'll do it here. As the thing locks and unlocks, the T-piece gets pulled forwards by its own camming motion, and then the spring applies the back force, the preload, onto the kinematic coupling. And that's how you get exact constraint. And yes, all of this will be open source. Motion system. I don't want to overlook the motion system because it's been a labor of love. I think 3D printer motion systems have been kind of lacking in the like super awesome area. The mid-range ones have been getting really good, but the like high-end, like really baller motion systems just haven't been coming out. So we thought we'd do one of those. Yeah, top plate. This is CNC milled aluminium because we had T5 tooling plate and a big milling machine, so we made it like that. People are like, why don't you water jet cut it? It would be way cheaper. Is that we don't have a water jet cutter, so like there's your answer. Here's some sort of pornography about how the thing's made. Everything for the XY system gets bolted onto this plate. So, and that's the carbon fiber thingamabob off to the side. But, so we have these standoffs. People are like, oh, those standoffs going to bend? No, they're steel, and the belt tension is not that high. And these standoffs stand the motor off of the plate. If we get into producing thousands of these, then we'll turn these 3 standoffs into an extrusion that gets cut to length. They do that already for NEMA 23 motors, but they don't do it for NEMA 17s. I don't know why. Someone should do that. Maybe we should just do that and sell it. You what, fam?
What?
Say again?
Are you talking about like how the NEMA 23 has the separate faceplate so you put screw in from like farther out?
Yeah. So you have a plate and you have a NEMA 17 and you want to mount and the NEMA 17 is like this and you want to mount the NEMA 17 like such. And so we're doing it with standoffs and screwing in like that into the front of the NEMA 17 faceplate. For NEMA 23s, there is available, pardon? Yeah, or whatever, and it doesn't really matter. Like we use screws that go all the way through from here all the way through, or do they just come through the back? They come in through the top and then they thread into the back faceplate like that. But what I'm saying is that in order to DFM this better and produce thousands of them, you could introduce a piece of extrusion that takes the job of those 3 standoffs. Anyway, let's not get into the details. This is how the lead screw motor attaches, which is pretty neat. So literally every single one of your motors, apart from the extruder motors, bolts to this. And all the motors are at the back. At the end, please do come along and have a look at the back over here. I don't think we've got a picture of the back in the presentation. I'm giving away all the... yeah, this is just a show off on the high wing rails, preloaded rigidity. You can like just flick with it on one side and there's no slop at all. I mean like no slop, none, 0. Yeah, this Gates GT2 belt is really nice. It's like faced with nylon. It wears a lot less. You know that like black dust that comes off the belts that sucks? This doesn't do that. It's also got way more aramid in it. This is, yeah, genuine high wind rails and carriages. This is the machine carbon fiber plate. To attach the rail to the carbon fiber, we have these press fit threaded inserts that we just, like, they're an existing thing, the well-explored science, so we just use those off the shelf. We actually turned our own bearing standoffs because, like, shoulder bolts, if you order them off Mizumi, they want, like, how much for them? Yeah, and I mean, if we can make a nozzle for, you know, €5 and a shoulder bolt costs you 10, then yeah, it's silly. Like, so we made those ourselves. Yeah, I like this image because this is the entire XY system, right? I love the core XY Fab Totem system. All the belts are planar. They sit on standoffs. You have 2 motors. They're right at the back. I think in the traditional implementation, the motors went here and here. We chose to make an extra. You need more idlers, but it means you have all the motors at the back of the machine next to the electronics, which is nice for EMI. Not enough people care about EMI, but we do. And so, yeah, these motors are all at the back with right next to the Z-axis motor, which is right next to all the motor drivers. So you don't have these high voltage, high frequency EMI off-giving things. Good, I'm glad someone appreciates it. And yeah, all the belts, like, they run parallel and perpendicular. Like, there's none of this, like, belts that are like this and stuff. No, we don't have that at E3D. We have parallel belts or orthogonal belts, with one exception, which is where the belt has to go round and it has to engage the pulley by, like, at least 50%. So yeah, it's really, really, really freaking neat. And it moves, like it moves. I don't know what the speed constraints are on it, but they might be your fault. Pardon? No? I want to see how fast we can push this thing. We just put, like, more motors in it. Like, it goes. It really, really goes. So yeah, electronics, working with Duet Rock. They do all this scripting stuff that allowed this to happen. They produce a great product. Big shout out to those guys. Could never have done it without them. So if you buy one of these systems, I thoroughly recommend you purchase the Duet and the Duet, what is it? Is it a Duet X5 or Duet X5 expansion board to run all the different tools? If not, I look forward to seeing what other solutions come about. Could be fun. Calibration. We can do it in 3 minutes. It requires calipers and a Mark I human eyeball. And in doing so, you can get 50 micron calibration alignment in X, Y, and 5 in Z. And the way you do that is you print vernier scales on the platform. Really simple. And then you come along and you look at the one that's most well aligned. And I would like these guys to implement in the UI the ability to touch which one is most well aligned and then set the offsets from that. So yeah, you print that, look at it, that's your offsets, done. And then you peel the thing off the bed and you measure it, how high the layer was in Z, and that gets you your Z offset, finished.
What if you put a camera on one of the tool heads, since the big box print bed already has?
Nearly there. Okay. Head's on the way. This head is the camera tool head. It has a Raspberry Pi in it, and it has a macro lens. So what we're doing with it at the moment, because the motion system moves and this tool head is light, within about 3 seconds we can go grab the tool, take 6 images, because it's a 300 by 200 bed, so we take 100 millimeter shots. The Raspberry Pi then uploads those to a server. Python script runs it, stitches them all together, and then once you've got the full print, the Python script runs it through FFmpeg, which means that you get a full video of your part being built, not from the side, but like you can see your infill being built and that everything is in place and everything is correct. So yeah, that's cool, and obviously a bit of OpenCV combined with that, and you're laughing. But that's Tony's problem, not mine, thankfully. The head on the right is the first pass at our flexible extruder. These are all Bowdens. Bowden, flexible, not really friends. But it's basically a NEMA 8 with dual drive gears, kind of inspired by Bondtech, that then drive it down here. This is V1, V2, we're like cutting everything right down short because flexibles don't need nearly as much cooling. Moving it to 3 millimeter. Yeah, there's going to be a flexible head, it'll rock, basically. So yeah, that's fun. Heads on the way, frickin' laser. So Greg is the founder of a company called Microslice. I don't know if anyone, does anyone have a Microslice? Or remember Microslice? It was on Kickstarter. It was the first desktop laser cutter. Laser diode, yeah. First desktop laser cutter to use a diode. So we would like to put a diode laser on a tool head. I don't really know what for, but like lasers. We think that we can maybe do subtractive with it on certain materials, like PET-based materials. We might be able to trim the edges. At the very least, we can mark parts with serial numbers or QR codes. So when we like start hooking this into automated, because one of these heads can also be a pick and place that picks the part off the bed and then dumps it onto the production line. And if you have it serialized along with your like calibration block, so you can print a dog bone in the same print and also etch that with a QR code. And so you know that your dog bone and your part were printed on the same print with the same material. You pull the dog bone, you verify. The aerospace guys will wet themselves, so it'll be great. And then this thing that we're crowning ASMBL, it's a bit of a handful, but you know, shortened to assemble. Additive subtractive manufacturing by layer. So we're going to add a subtractive tool to this. It's rigid. Come have a tap. It's really rigid. I mean, it's made of carbon fiber. It's rigid. So we want to put a spindle on there with a cutting bit, or you could have 3 or 4 of these tools and just one additive tool. Where that's a non-trivial project from the CAD CAM slicing side of things. If anyone wants to help, please give me a shout out. But I think that we can even cut under underhangs, overhangs. All these things are possible with things like lollipop cutters, and yeah, it can be done. We've got a lot of machining experience. We know how to do these odd things. I think it can be done. Inkjet for part marking again, and doing that XYZ Da Vinci thing, because apparently they have a patent on that, but like, I don't think it's a very strong patent at all. And I also think that there's a lot of prior art out there on the RepRap wiki, so screw those guys. But so we'll make the full color 3D printer thing. Hooray. Color's not really my game, but what I do want to do is be able to fire out a release agent that you fire out onto support material. So you can print same material support, and then you fire, because in terms of prior art, so there's a company called Rise who have, again, another patent on this, which is that they inkjet a release agent, a proprietary release agent, onto their proprietary material in their proprietary machine with their amazing software. Is junked, by the way, and they're actually, they came to us to try and fix some of their problems. So we told them to take a running jump because they're, yeah, they're really not such a great. Yeah, I won't get into politics. I think that patent may be indefensible, and also if you go back to Adrian Bowyer's like really early blogs, he was taking a paintbrush or a spray gun and putting baby oil on the top of the supports. Pardon?
Proprietary baby oil.
Proprietary baby oil. That's right. Yeah. So like something can be done there for functional purposes as well as part marking purposes. And then the cool one is pick and place. So this one really gets into the woods. So you know those pick and place things that use the coffee grounds in the balloon, and you have a vacuum pump and you like go onto things and you suck them up? Or we can print our own end effectors that are specific really quickly because we have 3D printers. What I would like to do is start off by, the first thing you do is you design a rack that holds all your vitamins, and not use those words in a while, but things like your bearings and your heat fit inserts and your pins and your springs and all of that kind of junk. Embedded electronics, PCBs, batteries, the lot. So you print a kind of dock on the bed, and then a human or robot arm comes along, because all these components come on tapes and reels and stuff like that for these kind of purposes. And then a robot head or human labor comes and places the appropriate components in this rack that the printer has printed. So the printer will print a rack on the bed. You know, for your 608 bearing, it will have a little hole in there that the 608 bearing goes into, and then, you know, your Raspberry Pi Zero here and the battery here. And so then you come along with your pick and place. So that's all built, you load it with components, and then you have a job that you build with the rack in place, and you can then come along with your pick and place tool, grab your head, grab your part, drop it into place, continue printing with embedded stuff inside. So that should be fun. Also a non-trivial software problem, but it can be done, right? It can be done. So I think that's pretty cool. I think that's... Yeah, you're damn straight. Like, that's, you know, what if Joe could convert his print farm to a print farm that doesn't just put out printed parts, but puts out printed parts with bearings and pulleys in it? How many humans would you be able to get rid of then? Pardon? Pardon? Yes. Yeah. Other thought, slicing for these things is we use Simplify 3D because we have to, with lots of processes and scripts and hacks and all of the rest of it. Despite this being a money is no object printer, in terms of design for manufacture, it actually came out pretty simple, right? There are 2 aluminium plates, one top, one bottom. There are 5 cut lengths of extrusion, one on each corner, plus a backbone for the Z-axis, 4 linear rails, 3 motors, some belts, some screws, and some standoffs. That's the entire machine. So in terms of DFM, that's pretty easy, because we can cut aluminium for sure. I'm sure humanity has a way of figuring out how to cut aluminium extrusion to length. These guys probably figured that out. But you get that to within, you know, 100 mic accuracy, easy peasy. Linear rails, order them from Highwind or whoever. On bulk, motors, dime a dozen. Belt, we've talked about. Screws, we can find those. And the standoffs we manufacture ourselves. Design for assembly, how long did it take you to build the second prototype that's still at home? How long? 10 minutes.
OpenRC is starting.
All right, I'm nearly done. Please fill in the survey. It's on the blog. If you fill in the survey and come to me, I will give you a free nozzle coated in the new magic coating. Yeah. That's it. Any questions?
URL.
Pardon?
URL. For the survey.
Ask her on the way out. Okay, we'll start here. You.
I was just curious, have you thought about putting like dip switches on there or something so it can recognize the tool head?
Yes, and in terms of bed leveling, we want to use the kinematic coupling as the switch and also as the bed leveling device, because kinematic couplings were like Renishaw touch probes. See you guys? Yes, basically. We can do it, it's going to rock. Questions? Make them quick, at the back. Shout. So it does that to the extent that Duet can detect skip steps, just like the Prusa Mark III can. It does not currently detect the heads falling off, but the heads do not fall off because they're positively interference locked in with the spring. If you really do something horrible, you can get a head to come off. The kinematic coupling, like you only have to be within about 3 millimeters, and then the head grabs within 3 microns, so we should be able to get that sorted. That's not a problem that we're having or seeing, but we do definitely need a way to detect that a head is present, and that comes with pogo pens. Yes?
So will you publish real, like I see real drawings getting used for a lot of your manufacturing stuff.
Yeah.
Will you publish real drawing that has real target sizes, tolerances, dimensions for the footprint for that on your website?
Yeah, it won't, like,
Great.
yeah. Yes?
If I do that, will that be in place through the US distributor, or is it transferred, or is it hopefully I have to have a ship from CPA?
I have no idea, but you can still have a nozzle. Yeah.
Different tool heads, what happened when you use V6 versus a volcano versus Mango volcano or whatever? Does it count for that?
Yeah, you just, in software, you set X, Y, and Z offsets.
No, switching heads on a single print.
Oh, you just drop the bed down, go back, dock it. You're all good. The only issue is on purging, because the purge brushes are at a specific height. So maybe we'll have to, I think the simple solution is that most people won't need a multitude of heights. So you just have one volcano one on the left and a normal one on the right. If you want to get super fancy, we could have like another Z-axis with a dump bucket that moves up and down. I know I'm going over time. There are some more, like, feel free to leave, but I've got some more crazy ideas that I'd like to pump out. So if you want to stay, stay. I don't want to screw up the OpenRC thing. Yeah. Yes.
So Bowden solution was partly as a means of getting the mass away from the hot end.
Yeah.
So now we're talking about multiple tools. Would they enable direct drive solutions back onto them?
Yeah. Basically, you can put whatever tool you want.
Great.
I don't know what the ultimate loading that the thing can take. My craziest of crazy ideas is that I want to get rid of all the wires and the filaments that come out the top of the tool heads, right? And then put a carousel in here, so you can have N print heads, and then you have a filament loader that is loaded with like 100 filaments over here. And then the printer goes up, picks up the print head, brings it to the loading station where the filament loader loads it in and fills the print head or the extruder or the whatever. And so then you can print with whichever material and whichever tool you so please.
Deal with thermal change in the layering in that situation. So think of it like this. The layer that's down, its temperature will drop by the time you get that loaded.
Yeah,
So now the adhesion between those two layers
Yeah.
is the problem.
yeah, maybe. Do you know anyone that's good at COMSOL? Yeah, it's a problem.
It's a great idea, but anytime
It's a problem. The solution is heated chambers, basically. There was one more crazy idea I had that I'd forgotten about. We did the camera, we did the thing. Oh, the vacuum. So one of the problems that we have, and BCN3D have the same problem, is that we do have to do a certain amount of purge and prime. And that purge and prime just like falls down here, as you can see, just kind of falls down there. So Greg is adding a solid, oh no, the solid state relay is already in there, but there's not a plug. And what we're going to do is link it up to a shop vac here. And so the Duet firmware will be able to run a macro that turns on the solid state relay, that turns on the shop vac. And so that when you're purging, it sucks the material off of the hot end, because then that scales, right? Then you can have a print farm of these things that scale. You can have a single shop vac. You can hook them all in. Duets are already got a great API on the back of them. So you can like build a server farm, not server farm, print farm, same deal, but manufacturing, not computing. And the other one is the pick and place tool, can also hopefully be used to remove parts from the bed and throw them onto a conveyor belt or similar, and they'll have QR codes printed onto them by the inkjet or laser head, and they go through. Yeah, it's going to be fun.
All of these parts are off the shelf, right? So even if you go with a more budget-friendly version,
Yeah.
would we would you have a list of what was used here if we wanted to go for like the premium version with the real?
Yeah, we'll publish the bombs.
Like every piece was off the shelf, right?
There are some turn parts for the standoffs and stuff, just because like we have lathes, and we could have used a standoff that was standard, right? But you'd have to wait next day for it to come, and you just press the button on the lathe, it comes off the thing. I think we keep doing that because they're still cheaper, just like the shaft bolts that they wanted $10 off Mizumi for. Arseholes. Yeah, I think that's me out and done. So thank you. Any more questions, come see me at the stand. I'm knackered. I'm hungry.